Go.
Right?
Hi, my name is Dr. Yu, and with my buddy Alex, welcome to our premiere episode of Physics and Media. Today, we're going to be examining the physics of the 2018 wonder Getting Over It. Getting Over It was the rage-inducing game that took over the internet for a short while in 2018. It consisted of a lone man inside a cauldron climbing up a mountain, even up to space. But let's say that the man was in a predicament. He's gone down the snowy cliff and is barely hanging onto the cliff with a sledgehammer. What would that take? For entertainment and aesthetics purposes, we will assume that the man in the cauldron is our buddy Vladimir Putin. His weight is 82 kilograms and has a wingspan of 36.3 centimeters. But what's more important is his shoulder width of 51.4 centimeters and has a height of 170 centimeters. With this in mind, we're going to be able to determine the dimensions of the cauldron. We're going to want a cauldron whose hole has a diameter of at least 51.4 centimeters. Why? Because at the beginning of the game, we notice our buddy Putin emerging out of the cauldron. Something not so easy to do if the hole's diameter is less than your shoulder span. We also know that the cauldron covers Putin's from below his ribcage. On PotGPots.com, we found a cauldron that would fit his dimensions. The pot is 55.88 centimeters wide, 55.88 centimeters deep, and 50.8 centimeters tall. This fits his dimensions that we need to put in it. According to the website, the cauldron weighs 72.575 kilograms, which puts our total weight at 154.575 kilograms. Then we might want to take this hammer into account, but that's actually not going to be the case. Do you know why? Because when Putin is hanging on for his dear life on that cliff, the cliff is going to be part of the hammer, not him. Our buddy Putin will be applying a force at point R. R will be where Putin's hands meet the handle, as that's where he's applying the pressure. We know that the arms are generally 1/2 the height of a person, so the center of gravity will be 1 meter plus 1/2 the height of Putin, or 1.85 meters away from the cliff. So now we've got our buddy Putin hanging off the cliff with his sledgehammer perfectly parallel to the cliff for this problem because Putin's an awesome guy. His center of gravity, or R sub 1, will be 1.85 meters away from his cliff. That means that we'll need to find a force of gravity pulling Putin downwards. Now that we know his mass is 154.575 kilograms, we'll determine the force of gravity pulling down with our good old force equals mass times acceleration equation. 154.575 times the Earth's acceleration of 9.8 meters per second squared means that we'll see a downwards force of 1,514.835 newtons. But that's not all, because Putin is kinda connected to the hammer, which rotates when gravity is pulling Putin downward. What this means is that we'll be using torque to determine the actual magnitude of force pulling Putin downward. The formula of torque is force times radius times sine theta. Because Putin is applying force perpendicularly to the system, theta will be a convenient 90 degrees and sine theta will be a convenient 1. So torque this time equals force times radius. 1,514.835 newtons times 1.85 meters as a radius, as that is the distance between a cliff and the center of gravity. We've got the final total of 2,802.44 newton meters. OMG!
Yes.
And in order for Putin to stay at the exact same position, he'll need to exert at least as much torque as gravity did. And Putin will need to exert much more force because his radius, R sub 2, is only 1 meter away from the cliff. Now that Putin's also applying a force perpendicular to the system, theta is 90 degrees and sine theta is 1. And that puts our needed counter torque as 2,802.44 newton meters times 1 times 1. This means that Putin will need to exert the same force of 2,802.44 newtons! We can convert 2,802.44 newtons to 285.96 kilograms to 630.44 pounds. That is the weight of 99 bricks or 23 gold bars stacked on top of each other, or about 6.5 toilets or 4 beer kegs, or about 2 panda bears on top of your palm. That is most likely enough to break your metacarpal or dislocate your shoulder due to your arm pressing so hard against your arm socket. But whatever the case is, your hand is screwed!